lecture. In this lecture, we will focus on maybe what you were expecting from the beginning on to talk about general relativity, and in particular, talk about the role of the principle of relativity, which makes the name of general relativity a part of it. Until now, we did focus on Newton's physics and special relativity. You will see today why did I spend a bit of time to try to explain all these concepts. But before we start, do we have maybe questions of the last two lectures that are important to highlight? Maybe there's something that was not clear. In any case, I will review the concepts that we already explained, and we need again a bit, but do we have any questions? Okay, it doesn't seem like it. Okay, so just to review what we did yesterday, because maybe it was a bit fast. So after explaining the role of special relativity, I try to make a clear distinction, a formal distinction of what we mean by covariance and what we mean by invariance. Okay, so let us just check again to have that clear, because it will become important for the discussion of general relativity. So let us assume that we have a coordinate transformation, okay, between two different coordinate systems, whatever they are. We say that associated to that coordinate transformation, there exists a transformation H that is an automorphism between M and M, where M is, remember, is the manifold, okay, of the space-time theory, such that this condition holds, okay. Then we can apply this transformation H to any object of a theory, okay. That could be the metric of the Minkowski space-time. It could be the extra structure we added to the Newton's space-time, and so on. So given any kind of object, we transform this object with this given transformation H, as I write there, okay, in a given coordinate. So remember, every transformation H is associated with some coordinates, and then we can write it like this. And then here comes the difference between covariance and invariance. We say that a given space-time structure, okay, is covariant under the transformation H if we transform all the objects of our given geometrical structure, and then this is also the same space-time structure, okay. Now, since we have written the different space-time theories in terms of coordinate-independent structures, then of course, in this formulation at least, it is true that H can be any admissible coordinate transformation, okay? This is not the case, of course, if we formulate both special relativity and Newton's theory in the traditional manner, let's say, with a coordinate dependence, with the inertial coordinate dependence. And then, of course, if we do formulate it in that way, the covariant group is not all the possible coordinate transformations, but either the Galilean transformations or the Lorentz transformations in the case of special relativity. But now we say, even if we formulate it coordinate independently, we say that a given space-time structure is invariant under the transformation H if all our given structures transformed into themselves, okay? Okay, so with that, I also briefly explained that both our Galilean spacetime and Minkowski spacetime, even though we formulated it in coordinate-independent way, there is something special about the fact that since both of them are flat, and we showed that the notion of flatness means that there exist some coordinates that allow us to define the different geometrical structures in a preferred way. So given this inertial coordinates, we can find the transformations that leave invariant the structures of both our spacetimes, and these are exactly the transformations that we expect both in both cases is the translation and rotations, which is the obvious. It's just let's say the static rotation and translation of our systems. But the big difference, of course, is that for Galilean spacetimes, the transformation that maintains invariant these four structures is the Galilean transformation, whereas in the Minkowski spacetime is the Lorentz transformation. Right there. Somebody has the mic on, please turn it off. Okay, so just a quick summary of both lectures again, in order to really take that for granted. So first lecture, we said we realized that there are some absolute notions. All started with Newton's mechanics, and he defined absolute space, absolute time, absolute motion. But then we realized that inherent to this theory, even Newton realized that in his different corollaries, the principle of relativity, that it dissolves the notion of absolute space. Okay, and then the way we have it is to incorporate inertial frames, which are also absolute. So, and that is always like with the principle of relativity in some way, it tries to dissolve some absolute structure, but never fulfills the let's say the final goal of relativizing or to dissolving any kind of absolute structure. Okay, that this is a bit of the philosophy which will become important for understanding what Einstein really was trying to do. We also saw that both Galileans and also Newton-Cartan spacetime, which this one involves the curved structure of the gravity, dissolves the need for inertial frames at the expenses of absolute geometrical structure. So if we want to formulate the theory in terms of independence of inertial frames, or if we want to think about in independent of coordinates, then we have to impose some geometrical structure, which one can reasonably say it's absolute. Okay, we cannot express in any meaningful way this geometrical structure in terms of relations between systems. So you see that even you are already seeing, and we will highlight this afterwards, you already see that there are different notions of absolute in what we are talking here, but there is still some notion of absolute, okay? Then in special relativity lecture, we saw that the principle of relativity, so Einstein took it back to the, let's say, to the big important principles of nature. The principle of relativity in the light of electrodynamics, so now we're thinking about electrodynamics, dissolves absolute time, okay? But we still have absolute inertial frames, okay, in the same way as we have with Galilean spacetimes. And then when we formulate it in terms of Minkowski spacetimes, of course, it dissolves again the notion of inertial frames. We can describe it in a general manner in coordinate-independent descriptions, but we have to add again this metric structure. And this metric structure, again, one doesn't have any argument to say that it's in any way relative or it dissolves, or no, it's really an absolute structure that we require in principle to describe the dynamics of the physical laws. Okay. One thing that I want to stress out, and this is historically important because it can lead to confusion. Now, in Einstein, we want to stress out that for Einstein, his laws, both in special relativity and also in general relativity, we will see that it was mostly algebraic. So what we mean by this is that he really was thinking of given equations written in some coordinates, and he was thinking of transforming this, how the different equations or the different dynamical laws transform with respect to given coordinate transformations. Okay, he was not thinking of in terms of metric structure or and so on and so forth. Okay, and we will see that because sometimes he refers to covariant transformations that he associates to Lorentz transformations because he's thinking of special relativity, not written in this general coordinate independent manner, but actually written in the manner that he proposed it in his paper, okay? Where we were, for example, we have there the typical expression of the distance measured by an inertial system in special relativity, and he was thinking of this kind of equation and proposing coordinate transformations to these equations, okay? Even though after the development of special relativity, Minkowski wrote it in terms of geometrical features. Really, Einstein did not take it too seriously, at least at the beginning, until and probably also until the final of his equations. Okay, so when he's talking about covariant, we will have to translate it into invariance, because if we want to talk about coordinate independent, as I explained before, Lorentz transformations are covariant only written in terms of inertial coordinates, and are invariant on the general coordinate independent formulation. And as I say, for Minkowski, geometric interpretation forces us to talk about invariance. Okay, so really, but okay, so with this, let us go for trying to understand general relativity. Now, I have to say that in comparison to special relativity has well-defined principles. Actually, Einstein thought about it as a principle theory in comparison to, for example, quantum mechanics, which would be a constructive theory in the sense that it had more to do with defining laws that were introduced to then explain experiments. Here, in special relativity, the principles he really wanted to be physical. He wanted to do something similar to general relativity, but as we will see, this is not the case. Okay, and even he introduced historically different principles. There is still today not a clear principles or the clear arguments on what is the basic structure of general relativity, and this is projected in the history of general relativity. During the decade that he was working on it, he changed a lot of different principles, and then he changed even more his opinions afterwards. So it's more difficult to understand really how to let's say intuitively go from one step to another in general relativity in comparison to special relativity. So today it will be a bit, hopefully not so much, but maybe can be a bit confusing because the different discussions lead to not a clear statement where I can tell you this is what Einstein had in mind and this is how he accomplished it. So sometimes Einstein had something in mind, but the way he accomplished it didn't have anything to do with what he had in mind before. But in any case, let us start from the beginning. So after the development of special relativity, Einstein clearly had in mind the fact that, well, on one hand, that gravity cannot be accommodated trivially to special relativity. One can see that by the fact that gravity is an action at a distance, so one have, in principle, infinite velocity of propagation, which is not is not according to special relativity a correct theory. But furthermore, Einstein had in mind, and this will be key to understand the whole lecture, is that Einstein really wanted to construct a relativistic theory where he could dissolve the notion of any privileged motion. Okay, for him, at the core of his heart, let's say, he really wanted to construct. Sorry, please turn off the mic. He really wanted to think of laws that didn't prioritize any particular motion. So remember, in special relativity and Galilean theory, in Galilean spacetimes, we have a preferred notion how to express the laws, which are the inertial motions. Okay, the inertial coordinate frames. You want to think about it. Now here he wanted to dissolve this in his way. So this comes parallel to the way he wanted to describe gravity. Okay. Okay, exactly like this. For instance, this would be embodied. Yeah. So the first thing he realized after the development of special relativity was what we now call the equivalence principle. Okay. So the first thing he started to do was to introduce special relativity in the form that he developed in terms of the Lorentz transformation and so on, and then try to do not inertial transfer, so Lorentz transformations to change from one inertial motion to another inertial motion, but actually see what happens if we transform the laws from inertial motions to accelerated motions, okay? So he started with the easiest case, which was the uniform rectilinear acceleration. And then he realized that actually there was an additional, in the laws of special relativity, there was an introduction of what he calls an homogeneous inertial field, okay? So knowing that as we saw a bit in Newton's Cartan theory, the fact that inertial mass and gravitational mass are just the same, he identified this homogeneous inertial field with exactly the gravitational field, okay? So he states here, we assume that a system K, inertial system in an homogeneous gravitational field, and K prime, uniformly accelerated system in gravitational free space, are physically exactly equivalent. That is, we assume that we may just as well regard the system K as being a space free from gravitational fields if we then regard K as uniformly accelerated. So what he's stating here is just basically the equivalence principle in core. He then continues and says, this assumption of exact physical equivalence makes it impossible for us to speak of the absolute acceleration of the system of reference, just as the usual theory of relativity forbids us to talk about absolute velocity of a system. Now, this is one who has to be very careful here because he's talking about uniform acceleration when he's doing the experiment. Sorry, somebody has the mic on. Please turn it off. But he really thought at that moment that the whole framework, the whole construction that he wanted to do had to do with the fact that he wanted to relativize acceleration, okay? The acceleration would be, let's say, as relative or as indistinguishable as, for example, absolute velocity in Galilean spacetimes. So he says this assumption, okay, that's I say. So let me just read here what Norton says, which I think is important in his paper. In this lecture, I will mostly follow the Norton's paper 93, which incorporates this discussion very clearly. So he said, both special relativity and classical mechanics, Einstein reported, suffered an epistemological defect. It was illustrated with Einstein's variant of Newton's packet. Two fluid bodies hover space. They are in an observable state of constant relative rotation about a line that connects them. In spite of the obvious state of constant relative rotation about a line that connects them, in spite of the obvious symmetry of the setup, Einstein supposed that one sphere S1 proves to be spherical when surveyed on the other S2 proves to be an ellipsoid of revolution. Classical mechanics and special relativity could explain this difference by supposing that the sphere is at rest in an inertial frame of a reference, introduced by Einstein into the argument as a privileged Galilean space, and that the second is not. This explanation, Einstein objected, violates the demand of causality, for these privileged frames are merely fictitious causes and not an observable thing. The true cause of the difference must lie outside the system. Einstein continued, immediately identifying the true cause in the disposition of distance masses. In effect, Einstein used this example to conclude that the only theory that could satisfactorily account for this example was one that satisfies the requirement of relative inertia. So what is telling us here is basically that for Einstein, any experiment that relied on the fact of an inertial frame to explain a physical law was not satisfactory, epistemological satisfactory, because we are relying on an explanation that has to do with something that we cannot observe, in this case, the inertial frames. So this sounds a bit too much to us, but actually the context in the history of philosophy of science, this concept was essential to the neo-positivists that started, let's say, the whole franchise of philosophy of science, because they took Einstein as very seriously in his way of thinking about science, and they really took this as the key feature of science, in the sense that as Einstein was trying, he already started with special relativity and then with general relativity, to really think about how we explain physical laws in terms of concepts that are not well defined, but they should be well defined, and they should actually refer to experience. That make the whole school of neopositivist of the like Reichenbach, Maurice Schlick, I don't know if you're familiar with them, but to use this as the key feature of constructing what, let's say, a good science should be, right? So historically, this notions that Einstein was proposing here is quite important, and that's why I highlight it, although we will not, of course, discuss this, but just so you know that actually philosophy of science in the last century started, like the key feature, one of the cores, started exactly by analyzing general relativity. Okay, so, well, you all...
Excuse me, Antonio. I think there's a clarification question in the chat that's probably a good point to ask. Someone is asking if you could explain a bit more what an homogeneous inertial field is. Perhaps if the person wants to unmute themselves and clarify the question, you are welcome to. So see that. So feel free to if you want.
Yeah. Can you hear me?
Yeah.
Yeah. So I wanted to, just the previous slide in which you say that this homogeneous inertial field. So why do you use the word homogeneous inertial field here?
Yeah, okay, good question. So I use homogeneous because we will see that well, one can show that it is in every point the same. Inertial is referring to the fact, I think that the label here refers to the fact that there is no force in principle involved. Okay, so we are really talking about here like the inertial fictitious forces in when you study like Coriolis forces. This label of inertia has to do with that. We will see an example so you can visualize what this means by inertial field. But really what it means here is that one can think of it as being as similar to the Coriolis force, but in this case, it's a field, okay? And that's how...
Now, it's like a following question that then there is written in the slide that he could identify this field with a gravitational. So that I need a bit more clarification. Identifying this inertial field with a gravitational field, that one.
Yeah, so I mean, of course, here one should check the paper and read exactly at which step he concluded that to really see the analogy. But you can see, if you think about it if you remember Newton's Cartan theory, there is, I mean, it will be obvious after some slides, we will show how he checked that. But if you think about it in terms of Newton Cartan's theory, if you remember, there is always that one could always, if you do some accelerating transformation, one in principle could show that that you can absorb it, let's say, in the gravitational field. So if you want to think about it, it's something like we did in Newton Cartan's theory, where we geometrize away the gravity field by knowing that the inertial mass and the gravitational mass is just the same. So here's something related, but don't take it completely literally here. What we are trying to do is just an introduction. Hopefully it will become clearer afterwards when we show the equations. Okay.
Okay, thanks.
Okay, so, well, you know how the equivalence principle work. I will not explain it too much. Basically, at least locally, we can do an experiment, for example, throwing a ball, and there is in principle two indistinguishable systems that physically have different descriptions. Apparently, in the first one, there is an accelerating system that is pushing the rocket upwards, and in the second one we have gravity. So we would say in the first one, oh, we have an accelerating system. So really, it's having this inertial force, so this is inertial field that Einstein was talking about. Whereas in the second one, we have gravity. And Einstein said, well, why are we saying that these two explanations look different when really they look the same, right? Okay, so now we're going really from how things were, let's say, published. So Einstein was trying to accommodate this whole idea during the first years of course, it's not that he was every day working on that, because at the same time he was working on other kinds of work in quantum physics and statistical physics and so on. But when he was traveling, I think he was in Prague before, and when he returned to Zurich, he worked with Grossman. Grossman is an important figure in Einstein because he helped him to pass the exams of his degree, and also getting work at the patent company. But he also helped him to acquire the mathematical tools he required for doing his whole idea of constructing a theory that was covariant, that didn't depend on a preferred coordinate system, a preferred frame. Okay, so he showed him the works of Ricci and Levi-Civita, where they constructed a theory that could be formulated in a way that was independent of coordinates. And that's exactly what Einstein was looking for. And then, well, you know more or less how this goes. We have some structure here, this quadratic differential form that you can show that is independent of transformation. So xn, if you transform x to another coordinate y, the structure remains the same. And this is exactly what Einstein needed to describe his theory. Now, one careful thing, and I will highlight this also after, is that Ricci and Levi-Civita really proposed their theory without thinking of the geometrical geometrical interpretations that this could have. Now, today we see this as some line element of a curved space-time, and we have all these completely rigorous notions of parallel transport and so on and so forth. But at that time, neither Einstein nor even the founders, Ricci and Levi-Civita, really thought about this being any geometrical interpretation of space-time. So Einstein, of course, wanted to work with special relativity. So he started with the line element of special relativity that Minkowski proposed. And he wrote this in terms of in arbitrary coordinates using this framework of Ricci and Levi-Civita, as you may know, in this formulation in terms of the metric. And then he took again this example he was trying to think about with the uniform accelerated coordinate transformations to really impose the principle of equivalence in this theory. And then he actually realized that by doing this, he would get a velocity of light that depends on the position. Okay, and then one could associate this to what he meant by this inertial field in this sense. Now, imposing physically that the equivalence principle holds, this line element, this new line element, was exactly what gravity was supposed to be. So remember, he wanted to describe gravity compatible with special relativity. So of course, Newton's laws were already, let's say, throw to the trash and see what happens new. Okay, so, and then what he was thinking, okay, I propose this new line element, at least at the birth, of course. Obviously, he had to add more stuff, but at the beginning he was thinking, okay, this new line element, taking the equivalence principle for granted, should be the description of gravity. Okay. Now, of course, as I say, this is just let's say a toy model, what we call today, because it's only referring to static gravitational fields, to uniform accelerated coordinates. So it's flat in any way. So you compute this curvature at 0. So it had to be generalized. Okay. Now, the way of generalizing is that exactly not taking for granted this line element, but taking a general line element like here in the last line. And then after some work in the paper that they wrote, I think in 1912 or 13, they proposed an equations for this metric that we would call it now gravitational field equations in this form. Now, here G, you are used to call it the Einstein tensor, but really at that moment, they proposed not the Einstein tensor, but the Ricci tensor as the tensor that would accommodate this equation, which in principle, if you think about it, is really the more natural introduction. by associating it to a stress energy tensor that has two indices. The Ricci tensor was the one that you were extracting from the mathematical description that Ricci and Levi-Civita had. And so they proposed that, but they realized soon that these equations didn't reproduce the Newtonian limit, okay, in the Wicca field approximation. And so they finally they proposed it, but they said it was not reproducing Newton's field limit. So at the end, they even finished the paper proposing equations that were not even covariant. So I think you have to think of that Einstein really didn't of course, he was playing around with different assumptions that he thought were important. But at the end of the day, physics is what tells you what is real or not. And then they say, okay, let's not take for granted covariancy to begin with. So after this paper, Einstein took another 3 years to really go back to coordinate independence. He struggled between these years. He had different reasons. I will not go into that, but you can find it in the Norton paper. He really was conflicted with the coordinate dependence or not, because he saw that if you really take covariant theories, that could lead you to some problems and then how to solve that and so on. But let's admit that at the end of the day, he really accepted coordinate independent covariancy, and then he proposed the Einstein's equations with the Einstein tensor as we know today. So before I continue, just a small parenthesis. As I said at the beginning, I think it's a misconception, and this was stressed by Dennis Lemkool in 2014. And I think it's really nice to read it, because usually when we are taught general relativity in the school, it's always one kind of typical formulation, this very geometrical formulation. But if one sees this in perspective, this was really not what Einstein was thinking at the time. It was accommodated later, most probably after the 60s, where all the Penrose, Hawking, and all these kind of figures really took this as a geometrical interpretation. But really, Einstein never thought about this in that way, not in the start, and even not at the big after he developed the theory. So I refer to you to that paper because it's very nice how he had a lot of discussions, and you can clearly see that Einstein was really philosophical, guided all the time, even after he developed his theory, because he never completely was satisfied with it. And he was always trying to discuss the different principles and the different foundations of his theory. So this is a letter he wrote to Reichenbach. Reichenbach is one of the founders of this neopositivist school that I was talking about before. He says, "You are completely right. It is wrong to think that geometrization is something essential. It is only a kind of crutch for the finding of numerical laws. Whether one links geometrical intuitions with a theory is a private matter." Okay, of course, one can say, okay, this is only one text, but in the paper you can find more arguments that he gave and more texts where he really rejected this whole idea. The only geometrical interpretation he gave was to say that that bodies move following, let's say, for example, a curve. Okay, that was his own way of thinking about geometry and accepting the fact that you can define some geometry, but never really a geometry of space-time on its own. Okay. What he did believe is that his whole framework of the equivalence principle, what it's trying to do is unifying gravity and inertia. Okay, this is the key point. This is what he really thought it was the important feature of general relativity in this aspect. And he basically stated this in the geodesic equation that you can write in coordinates. So you have two terms. You have the left-hand side, which would be in some way what we would call an inertial contribution, if you think about in terms of special relativity, plus the extra term that you may call the gravitational part. Okay, that how exactly he explained it. But this distinction is just apparent because if you change coordinates, now, the whole geodesic equation is maintained, but obviously both terms, by definition, by construction, they are not invariant on the coordinates, so they mix each other. So talking about inertia in one sense and gravity in another sense was not is not true. It's just an apparent, let's say, fiction. And he put the analogy to that with exactly what he thought of electric and magnetic fields, because electric and magnetic fields, when we interpret it in terms of Lorentz transformations, they dissolve in a similar way. We have to talk about electromagnetic fields, and we can only talk sometimes about electric and magnetic fields given some coordinates if we want to compare it with, for example, non-relativistic cases. And he thought this was the similar thing. So you could talk about gravity and inertia if you want to compare it, for example, with Newton's physics to the Newtonian limit. But the moment you really accept general relativity, this unification of inertia and gravity it was very similar to how electric and magnetic processes were unified. This is what he writes. Formally, the unity between inertia and gravity is expressed by the fact that the entire left side of this equation is tensorial with respect to arbitrary coordinate transformations, where the two terms parallel are not. In analogy to the Newton's equations, one would have to view the first as an expression of inertia, the second as an expression of the gravitational force, but only in analogy to Newton's equations, not really as a key feature. The existence of electric fields is a relative one, depending on the state of motions of the coordinate system. Only the electric and magnetic field together can be attributed a kind of objective reality, independent of the state of motion of the observer. And this is exactly the case of inertia and gravity. And then he also says, then I had the different text. Then I had the most fortunate thought of my life in the following form. The gravitational field only has a relative existence in a manner similar to the electric field generated by the electromagnetic induction. Because for an observer in free fall from the roof of a house, there is during the fall, at least in his immediate vicinity, no gravitational field. Namely, if the observer lets go of any body, they remain relative to him in a state of rest or uniform motion, independent of their spatial, chemical, or physical structure. So if you remember, Einstein started the special relativity by thinking of this way of describing electrodynamics in terms of two different ways, which for him is just the same thing, and it had to do with the relativity of motion. Well, here it's just exactly the same, but with inertial motion and gravity. Okay, so you see, like, he was very conservative in this way. He was just following what he already successfully discovered with special relativity. By the way, just to you know, so a lot of these texts have also actually are very recent, because Einstein wrote them, but we didn't have access until like this last decades. And you can find a lot of these letters and the way he thought if you're interested in this kind of discussions. And there's the collected papers of Einstein, which you can find online. They are all published online, open to everybody. So if you ever want to read about it, it's all there. Okay, so just to add a bit extra, to really get a grasp on the equivalence principle. Now you couldn't tell me, okay, we saw that actually, as I said before, Newton's Cartan formulation it had incorporated the equivalence principle already in some way. Okay, so basically, by the way of writing the theory of both inertial, if you want to think about it in terms of the quality for 0.2 per 3, we have the right hand side, the quality there. We have a gravity field that would be the right hand side, and the left hand side would be the inertial structure in some way. We can just put it together and write the left hand side, where there is no identification of what is gravity and what is inertia. Now, that's true, but I think we must stress out here, I think the key of understanding what makes that general relativity distinguishable from Newton's mechanics in this sense is that actually general relativity forces us to think the principle of equivalence is very important for the description. Newton's mechanics can be formulated without invoking it. So in actually Newton never really took it as an important feature of his theory. He could develop exactly the same formulation without it, and that's exactly what this equivalence from shows. Now, general relativity doesn't allow us to do that. We cannot write the geodesic equation in curved spacetime in relativity as a scalar field or whatever other field as acting as a force. So in this sense, really general relativity is explaining us in some way, if you want to think about it, the principle of equivalence. Or in other sense, it has more power in the sense that the principle of equivalence comes hand by hand with general relativity. Are there questions until now? Maybe
There's one
Yes,
left
I-
in the chat.
Okay.
I'll read it for you. It says, I didn't quite understand how Einstein solved the problem of considering inertial frame. I mean, what he changed so that it wasn't necessary to consider it anymore.
So, sorry, I didn't fully understand.
Yeah, so I think the question is, why is that unnecessary to consider an inertial frame to develop Einstein's relativity?
How is it unnecessary or necessary?
Unnecessary, yeah.
Unnecessary.
Well, the person who asks is free to unmute themselves if they
Yeah.
so wish. Yeah.
So I think that the important is not that it is unnecessary, is that it's it's a relative concept. It's dependent on it's you have to think about it. The analogy is like absolute velocity in some way. So here an inertial frame for Einstein it doesn't have any meaning because you say, okay, what is an inertial frame? An inertial frame is something that it's not accelerated. So I can differentiate between accelerating and not accelerating. And I say, okay, an inertial frame is really an absolute notion because it's I can define it. It's something that is not accelerating. Now, for Einstein, this doesn't make sense because he says, well, I can always take an accelerating system, put gravity on it, and then it's not there anymore. So there is no way of saying you are in an inertial frame with gravity or you're in an accelerating frame without gravity. So this distinction it dilutes the notion of inertia in some way for him, at least at this point. There is no physical way of showing that you are in an inertial frame because it always could be possible that you are just experiencing gravity, and then you could say, oh, I'm an accelerating frame, or am I in an inertial frame with gravity? For Einstein, this question then it was dissolved because it didn't make sense. There is not absolute way of defining this.
Sorry, if I may. Yeah, I think I get it now. Like it's just that by the time that he had only special relativity, it was like he was still dependent on inertial frames and he wanted something more general. So with the principle of equivalence, this inertial frame problem went away. That's all.
Yeah, exactly. So as I said in the beginning, Einstein was thinking in two things. One, how to include gravity in the special relativity picture. Two, how to generalize the special relativity to any kind of motion apart from inertial frame. So that both of these ideas were where he was guiding him through, and with the equivalence principle, in some way, he was connecting both ideas.
All right, thank you.
Okay, so now I said more or less what Einstein was trying to do. At the end of the day, he constructed a theory, and now after the publication in 1915, a lot of discussion came after to think, okay, did Einstein really accomplish that? Did he really relativize motion as he was his dream or not? So as we have seen, Einstein was convinced that inertial motion is not absolute. An accelerated uniform motion can be interpreted, it is indistinguishable from an inertial motion with a gravitational field. We can make it more precise in the sense that some people say, well, okay, that principle of equivalence basically tells us that at least locally we could have a notion of flat spacetime. So we can always choose coordinates to erase the gravitational field, at least locally, okay? And at least for Einstein, this was at this point enough because he could fulfill his idea. Now, the problem is that people realize that quite straightforward is that actually, even though that's true, we still have a absolute notion of acceleration, which is exactly how we define the geodesic equation. We equal it to 0 if it's free of forces, but if it's not free of forces, and for example, if we have an electromagnetic field, then we have an acceleration, and this acceleration is completely coordinate independent, so it's absolute in that sense. Okay, so it is not true that all motions are completely relativized, and there is no way of saying, is this accelerated or is it not? Because we have a way, if we don't have, if we have extra forces, which, for example, electromagnetism is clear. Now, I think, and Einstein was what he was really thinking at that time, and I think maybe he took it even for granted that he would at some point reach to that point, was that he was actually trying and at some point to unify gravity with electromagnetism. So at his time, he thought that electromagnetism was the only extra fundamental interaction apart from gravity, and he tried to do it after he's developed GR to unify electromagnetism with gravity. And I think if you could in some way think about it in terms of geometry, that's not how he thought, but if you think about trying to geometrize away electromagnetism also, to incorporate it, then of course the acceleration would not be 0, not 0, it was 0 in this case everywhere. So if you think it out that picture, maybe it makes sense. But since this theory was never accomplished, and we are based on general relativity plus some other forces like the electromagnetic force, then the notion of acceleration is still there. And it's still absolute in the sense that it is coordinate independent, and for any kind of body that is moving, we can say that it's accelerated or not accelerated. Okay, so let's say that dream of Einstein was not completely fulfilled at this level. Now, no, I think how Einstein tried to solve this was taking, okay, it's true that you have a notion of acceleration, but the difference here with respect to general relativity, sorry, with special relativity and with Newton's physics was that acceleration, if we go back, it depends on the covariant derivative, which at the same time depends on the metric, and the metric depends on the matter. So this chain made us say, okay, it's true that it's absolute, but if I could explain this acceleration by means of the matter distribution of the universe, then I could say in some way it's relative. It's relative to the matter behavior. And actually, he was influenced a lot by Mach, because Mach, even before Einstein, really took this as a core feature of physics, and actually he criticized Newton of his position on absolute space and absolute motion by exactly taking the idea that in principle inertial motion could be described in terms of the matter of the universe. Now, even though that was a philosophical claim, he never could completely construct such a theory. But Einstein took this as a key feature, at least in this argument, and say, okay, then the argument goes as follows. In terms of motion, I can differentiate between accelerated motion and non-accelerated motion, but the accelerated motion depends on if I can show that it depends on the components, on the composition of the matter that surrounds this, then I can give an relative explanation to the accelerated motion. Well, here is the, okay, I will not explain this because this is basically Mach's idea of the bucket experiment. I'm not going to explain it, but if you want to, I can do it in the question section. He took his equations of gravitational fields, and that was exactly what he was trying to do. He was saying, okay, again, I need the covariant derivative, which depends on the metric, which is incorporated in the geometrical, in the Einstein tensor, which depends on the matter component. So in some way, there is some influence there, right? Now, of course, this was not achieved, and one can see that in many ways. The one way historically that he saw is actually that the Minkowski spacetime, was a vacuum solution. So even in the absence of matter, I have the Minkowski spacetime, and the Minkowski spacetime gives me a preferred inertial motion, an absolute notion of acceleration. So actually, Einstein fought a lot with this idea. He actually tried to erase from the theory Minkowski solutions by adding a cosmological constant, for example. But then, of course, as many of you know, the sitter showed that even if you add a cosmological constant, you can actually get solutions of the equations of Einstein's equations, and you have the same problem again and again. So even in the absence of matter, now today we know that actually there is a whole tensor, the Weil tensor, that doesn't depend on the matter components, which is telling us something about the metric. So it's not completely determined by matter. But of course, at that time, Einstein was not so aware of this, but he already realized that by these clear examples, even if he tried to say that some solutions like this were not physical and so on and so forth, but at the end of the day, he had to accept the fact that the metric, and therefore the covariant derivative, and therefore the geodesics and so on, didn't completely depend on matter. So it was still absolute in that sense, and it could not be replaced by anything else. And you can see in some text, I will not go for it, that actually Einstein never took for granted anymore the Mach's principle, and just didn't took it as a key feature of general relativity. Okay, so we have said something that make us think that the principle of relativity is nowhere to be found in general relativity. We have seen that the coordinate independent formulation doesn't really make something that relative special about general relativity, because Newton's theory can be described in terms of it, special relativity also. Their absolute acceleration is still there. So actually, that was the feeling for some time. And here's Sinch, one of the most famous relativists of his time. He says the general theory of relativity, the name is repellent. Relativity, I have never been able to understand what the word means in this connection. I used to think that this was my fault, some flaw in my intelligence, but it's now apparent that nobody ever understood it, probably not even Einstein himself. So let it go. What is before us is Einstein's theory of gravitation. So really there is no principle and only a theory of gravitation, okay? Like quantum mechanics could be a theory of matter. The geometric way of looking at space-time comes directly from Minkowski. He protested against the use of the word relativity to describe a theory based on an absolute spacetime, and had he lived to see the general theory of relativity, I believed he would have repeated his process in even stronger terms. So Sinch was here really telling us that forget about the principles, forget about these relativity notions, really concentrate on the geometrical construction of the theory that we have been given by Einstein, and just assume that this geometric structure is absolute in the sense that it's there, it explains the space-time, and just keep up with it, okay? I see the chat growing. Is there any question that I should answer? I think it's a good moment now. Okay, I see not. Okay. So one can, of course, take this position, thinking, okay, let's just accept the fact that the theory doesn't tell us anything about the principle of relativity, and it's just maybe a guiding principle that historically Einstein had, but at the end of the day, it doesn't make sense. Or we can try to keep up with it a bit more and try to desperate in some way to say something about the principle of relativity and why general relativity is so different from other theories, apart from the fact that it explains gravity and electrodynamics and so on and so forth. In order to do that, I want to briefly give you some definitions to properly say something about the principle of relativity. So I will use these three definitions of absoluteness that Friedman proposed in his book, in the 83 book. that are important for our distinction, okay? So first of all, we have the notion of absolute versus relational, okay? Here we are speaking really about an ontological notion. So he says, well, whatever theories ostensibly about space-time structure are merely theory about spatial temporal relations between physical objects or whether describe independently existing entities. So what we mean by this is that do theories provide us some absolute notions that cannot be explained in terms of relations of objects, or are any kind of object that we impose to spatial to space-time something that we can define in terms of relations between objects? So this claim was really historically important, because I think I maybe said a bit about this in the first lecture. The contemporary thought, philosophical thought of Newton's historical moment was really about the more relational approach, where in principle time or space or motion were concepts that could only be defined as relation between objects. Okay, and in that sense, Newton was really going against this thought by imposing some absolute structure. So one important distinction is this, but then maybe we are more interested in these two other ones because they affect more the physical theories. So we have absolute versus relative. It says if a given structure defined independently, of reference frames or coordinate frames or not. So if it's absolute, then we can define it in terms of coordinate independent ways, and if it's relative, then it's not. For example, we could say that absolute space, if you remember, we define it in terms of this vector field, then that's a completely absolute structure because it's independent of coordinates, but so is the metric in this definition because they are independent of reference frames. Whereas, for example, relative notions is, for example, this inertia gravity distinction, and the Christoffel symbols, if you want to think about it, because the Christoffel symbols, you could incorporate the gravity forces they are dependent on the reference frames. Another notion, of course, is time in special relativity. Okay, it depends on which inertial frame you define. And then is the last one, which is maybe slightly different from what you would think is absolute, and it's the absolute versus the dynamical category, and it's basically telling us that but it does depend on the matter. Sorry, the record was stopped. Okay, great. So let us make clear these three distinctions. And here is a nice schema that one can think when one trying to take Einstein seriously as trying to relativize something. And it's okay, what do we really relativize? So one can start with the most strict notion, which would be the first category, and say, no, any kind of space-time structure is just is just what we say here, relational. So it's just a relation between matter, which we call Leibnizian relation, because actually Leibniz was Newton about that. We want to relativize motion in this way, which was also in some way Einstein's dream, at least at the beginning. And then one could think about this and realize that it's actually very not clear how to do that, because we still need some notion of space, time, and motion. We cannot just express it in terms of matter. But then, okay, let's say we go a bit further and say, okay, we don't relativize in that way, but we try to relativize all kind of motion. So in the sense that and this was also Einstein's dream, that, okay, if we define covariant independent formulations, then in some way, absolute notions would dissolve, okay, like acceleration. And we saw that this was also not true. So no absolute motion in the sense of 2 is also not true, because we still have an absolute notion of acceleration that is independent of coordinates that I have shown. So that doesn't work out. Actually, Friedman, he says, dotted lines indicate unsuccessful programs. They were programs trying to work, but they did not work. The parallel to that is, okay, saying, true, no absolute acceleration can be, so sorry, there is an absolute acceleration, but I can say that it depends on the matter structure of the universe. That is called like what he calls Machianization. So using Mach to work with that. But actually, as I showed you, it's also unsuccessful, because we cannot express the metric fully of in terms of the composition of matter. So what we have left, if we don't have the first definition, the second definition left, we can only try to do something with the third definition, okay? Because this is true in GR. So general relativity, the affine structure, depends on the distribution of matter dynamically. So it is really not absolute in this third definition. So this is the, let's say, or trying the last chance we have to take the principle of relativity as a serious thing. So I will now try to explain the manner we can do that. But I think maybe we can do before this a 10-minute break, if it's okay with the organizers.
Yeah, it's okay by me. Anyone, does anyone have a question to ask before we break?
Yeah, if we have questions, we can use this now.
Okay, apparently not. So we reconvene in 10 minutes.
Yeah, great, thanks. Okay, so just to recapitulate, because now comes a bit like the hardcore part. So remember what we were trying to do. We were trying to think that after Einstein accomplished his theory, and he developed this theory thinking a lot about this principle of relativity, and it has already started with special relativity, and he was really trying to go with it until the end. We saw that in principle, at least the naive notions of relativity do not make sense in his own theory, at least how he proposed it. But we still want to find a way that makes sense to say that the general relativity differentiates itself from the special relativity and the Newtonian theory, apart from the fact that, of course, it explains more physical theory, more physical effects, and we know that by far, and you know that more than me. But really, in the core, as Einstein thought about it, relativizing completely something, and we want to try to think if we can see that in the last option we have to say, because the other two definitions didn't work out. So we know that the metric of general relativity is the only special thing that we can think about it is that it is affected, not completely determined, but at least affected by matter. So let us see how that has an important role or not. So before I do that, let me come back again to the last thing I said in the second lecture. So you remember that there was something special about both Galilean spacetime and Minkowskian spacetime, because even though they can be written in a coordinate independent manner, there is something special that you can always find coordinates that can be written in another formulation, which is the standard formulation that you work with. And this formulation has underlying symmetries, which gives us exactly the whole notion of inertial frames being transformed one to each other by these given transformations. In the case of Galilean spacetime, by Galilean transformations. In the case of Minkowski spacetime, by Lorentz transformations. And it incorporates the fact of the principle of relativity exactly in this way, saying that different inertial frames see the same physics. So here's the core idea of these two theories. So there is two things here to think about. First, that we have a given formulation of the theory that is coordinate independent, but it looks like the coordinate dependent way in terms of inertial coordinates seems to be preferable. actually Einstein, so historically, Kretschmann in 1917 showed that a bit what we were discussing, that Newton's theory and special relativity can be written in a coordinate independent way. He contacted Einstein, and Einstein's response was, yeah, okay, this is true, this is beautiful, but it's not the simplest answer. The simplest answer is still the initial formulation that we all know. And he was in some way right, because it's true that in this formulation, you can clearly have the notion of inertial frames, and you can clearly see that the transformations that live invariant the space-time structure are exactly the transformations that underlie the different transformations between inertial frames. Okay, so let us keep that in mind, because it will become important, because here, at least in this case, we have really a notion of principle of relativity. Now, it's not the dream of Einstein's principle of relativity, because he wanted to extend it to all kind of motions. Here we have a restricted kind of motion, which are the inertial motions, but at least we can incorporate the principle of relativity in a physical, meaningful way in these both theories, because the principle of relativity states that two inertial frames see the same physics. Okay. So here I want to stress out, I think, a really interesting aspect, that because this discussion, and you can see Norton paper, it came a lot back into the arguments of Einstein and other physicists at the time, back and forth about the importance of relativity, how to define the principle of relativity, and the different books you can take, all of them, none of them really agrees on one way of defining the principle of relativity. As you saw, Sinch even said that there was no principle of relativity, and so on. So one of the interesting quotes from Elie Cartan says the following: general relativity threw into physics and philosophy the antagonism that existed between the two principal directors of geometry, Riemann and Klein. The space-time of classical mechanics and our special relativity are of the type of Klein. Those of general relativity are the type of Riemann. What does Cartan mean by this? Well, the notion of invariance that we saw here is actually Klein's program. I think I commented this a bit on yesterday, which was also Minkowski's program, because Minkowski was, I think he was student of Klein, which had all this idea of relating geometrical structure with invariance on the transformations, under some group transformations. And this is exactly how this is expressed here physically, actually, in the Galilean and Minkowski spacetime. Whereas general relativity looks more, not so much of an invariant theory, but more of a Riemannian theory in terms of geometry. So Cartan was stating this fact that there seems to be this difference between the two theories, which Einstein, I would say, maybe trying rejected, because he never really thought about GR being a geometric theory, but actually trying in some way to be invariant under general transformation and making this physical significant. Okay, so how can we try to unify these different ideas? How can we make sense of this puzzle? So a beautiful, nice intuition proposed by Ehrman and then updated by Friedman and Jones, is the following. We can define the principle of relativity as an equivalence of various states of motion, that is, of various frames of reference. Okay, this is the whole idea of the principle of relativity in special relativity and Galilean space-time and Newton's theory, as I have said before. Let me read here. The essence of the principle of relativity in the special theory is the indistinguishability of all the inertial state of motion. Thus, Einstein in 1995 special relativity paper had been motivated by the realization that no experiment in mechanics, optics, or electrodynamics could reveal the uniform motion of the Earth through the ether. That is, space and time look the same experimentally to observe it in any state of inertial motion. Einstein's task was to devise a theory in which they look at the same theoretical as well. So this is the core of what I explained before. So you had some invariance, some physical invariance of the frames, and then you were trying to create laws that were exactly describing this and making the laws give you the transformations and making exactly this invariant theories under this transformation. So both physics and the mathematical formulation get together. So let me read here how this experimental idea is. This condition can be broken up into a kind of pseudo-experiment. We begin with an inertial observer who performs a range of experiments in kinematics and other branches of physics. The observer is then boosted into uniform motion with respect to its original state of motion and carries along with him a complete record of all experiments and their outcomes. These experiments are now repeated and the outcomes compared with those of the original set. The principle of relativity requires that both sets of outcome must be the same, and a theory satisfying the principle of relativity must predict this will be so. Okay, this is experimental. This is the physics we would like to explain. How is it the theoretical way? Well, exactly as explained. We have some geometrical structure, and we force itself to be invariant under some given transformation, which will be the one that connects our different frames. In the case of Minkowski spacetime, these are exactly the Lorentz transformations. Okay, and here this H transformation is exactly as I said, how we transform inertial frames into another. Okay, so this whole picture is very clear in special relativity. It only is valid for inertial frames, for inertial motion. That's true, but it is very clear here how to connect the physical principle of relativity with the theoretical notions of invariance and the transformations. Of course, this is if we only think about geometrical structure. So in special relativity with the manifold structure and the metric structure, this is not enough. In general, with experiments, we need more. We can have an electromagnetic field, we can have mass density, and so on and so forth. So for general cases, the way we transform with this invariant transformation is the following. So we start on the left-hand side with some manifold structure, some metric structure, and then some other kinds of tensors. These tensors can be the stress energy tensor, it can be the electromagnetic forces, it can be mass distributions, whatever you think. And then when we use these invariant transformations that leave the metric invariant, of course, it transforms the different extra structure that we have added. Now, how do we follow with the principle of relativity? The principle of relativity requires to consider the transformed quantities as indistinguishable from the original ones. The principle of relativity is nothing more than equivalence of inertial frames of reference. So if one theory with like the left-hand side with the whatever components you add with the whatever electric field or magnetic field and so on, is the transformed quantities via, for example, the Lorentz transformation in the case of Minkowski spacetime, have also the same right to be correct, okay, in any physical situation. So this is the principle extended to kinds of other kinds of fields. Now let me read. The basic moral of the work of Ehrman, Friedman, and Jones is that there is no natural sense in which this equivalence obtains in the spacetimes of general relativity, and that there is certainly no extension of it to accelerate the frame of reference. So when we're trying to apply this to general relativity, it completely fails because it's not true that we have some invariant transformations. In this sense, there is no principle of relativity in the general theory of relativity. This moral follows immediately from the fact that special relativity admits non-trivial symmetry groups, the Lorentz group, which match inertial frames of reference into one another. The spacetime of general relativity in general admits no symmetries. In general relativity, the closest analog of an inertial frame of reference is a frame in free fall. It's represented by a congruence of time like geodesics. In general, a transformation that maps one freely falling frame of reference into another will not be a symmetry of the metrical structure. So if we try to find an H that transforms the metric as in Minkowski spacetime, we will find none. Therefore, spacetime observers of the first frame will see different metrical properties in spacetime than will those of the second. This indistinguishability required for the equivalence of frames does not obtain. Considering arbitrary frames of reference rather than those in free fall clearly does not change this result. So here is really what is the key failure of that idea in general relativity. So what was special of special relativity in Galilean space-time, the whole idea that we have some transformations that would leave the objects invariant, and I think maybe this was Einstein's dream, if he would mathematically try to formulate it, is not accomplished in general relativity. Okay, general relativity can be written in a covariant independent manner, that's true, but because it doesn't have any invariant transformations, and that this is completely clear to in some way to Einstein, because he himself admitted that there were no inertial frames. So in some way, it makes all sense, but of course, it is not what he wanted, because he wanted really to establish this principle of relativity. Now, here comes the interesting part, for like the last part of the lecture of the course. So I continue. The real puzzle then is to determine the sense in which Einstein believed equivalence to be extended by general relativity. There is one reading in this geometric language that does allow a general equivalence of frames. So far, it has been assumed that the background spacetime is represented by the combination of manifolds ametric in general relativity. If instead one takes the manifold alone as the background spacetime, then one immediately has an equivalence of all frames. Obviously, remember that the covariant group of all admissible coordinate transformations left the manifold structure itself. So that's true. It didn't left invariant the metric. For considering just manifold for simplicity, an arbitrary automorphism is a symmetry of the manifold. Since any frame of reference can be mapped into any other by an automorphism, it follows that each frame sees the same spacetime structure, so that they are equivalent in at least that sense. So if we do the trick of taking away from the spacetime structure the metric, then we fulfill Einstein's dream, because obviously the manifold structure, the most basic fundamental structure, is invariant under all the possible coordinate transformations. If this equivalence is to be extended to the sort of equivalence of the principle of relativity of special relativity, then the metric tensor field of general relativity must be treated in a similar fashion to the other structures, like the electromagnetic field, the mass distribution, and so on, of the above discussion of special relativity. Then a similar sense of equivalence of arbitrary frames follows directly from the active general covariance of general relativity. So if we have a frame 1 of reference, which sees the metrical field G, and another field and other kind of fields, whatever you want, we have some like that is the following model in one reference frame. Then in another reference frame, the theory must allow a model in which F2 sees an identical configured set of fields. That is, if H is an automorphism that maps F1 into F2, which here is the full covariance group of all coordinate transformations, then F2 sees the following model. And that's exactly general covariance. So we have, if we don't think of the metric as being part of the spacetime structure, underlying spacetime structure, if we assume that, which is a very tough thing to assume, but if we assume that, then we do fulfill Einstein's dream, because indeed the spacetime structure is invariant, and we just have to transform all the other things that we put on top of the spacetime, like the metric, to transform in this way. Now, if one think about it, one can argue, yeah, that's completely true, but that doesn't help at all, because Newtonian physics and special relativity can be defined in exactly the same way. So we have fulfilled one dream of Einstein, which was relativizing in this sense the space-time structure, because Einstein historically, one can find texts where he actually argues that the metric is nothing special. The metric is just another field, like the electromagnetic field, and they can have the same category if you want to think about it. But of course, as I say, this does make GR special. Now, but now if we remember Friedman's definition, and this is exactly how he defines it, and also he took that from Anderson, a physicist that wrote a very nice book, which I recommend you, about general relativity. And it's the fact that as I said, the only difference of the metric in general relativity and special relativity is that the metric is dynamical. So if we take this as our discrimination, what we can say about this is that what makes special general relativity is the action-reaction principle. So since the metric depends on the matter field, it is not absolute in this last sense that Friedman says. And then we can actually say it's not absolute, so let us retire it from the space-time structure. Okay, so the key feature to understand the whole picture, if we want to really keep in saying that this makes sense, is that okay, in special relativity, we have the Minkowski spacetime, and in the Minkowski spacetime is an absolute by definition, because it's not dependent on the matter structure like the metric of GR is. So in that sense, it's an absolute structure. So it is part of the spacetime. And then we have the properties of the invariance group of the Lorentz transformations. Now, what GR is really telling us, if we really take this as the core, which then the metric is no longer absolute in this third and last definition that we had, which forces us to take it off of the space-time structure. And then we can make sense of the whole principle of relativity of the full covariance group and Einstein's theorem, okay? So if we want to impose or philosophical, metaphysical, whatever claim you want to think about this that Einstein had, then we are the only consequence that we have is to accept this fact that the metric then can be categorized in the categories of other kinds of fields. So as I said, exactly, this is the whole point, to connect both of these notions. Of course, this has more arguments than I explained here. And as I said, in Anderson's book and Friedman's book, they really make this concise. They really say what is absolute, what is not. They really give a mathematical framework in order to explain that. Of course, here I was very, very briefly just to maybe provoke you in some way. But of course, this is way more developed than what I have done here. So let me here finish. The only way to say the relativity principle of general relativity forces us to conceive the metric as a dynamical, non-absolute feature, and by consequence of our definition, retired from the space-time background structure, and put it together with the rest of the geometrical objects and matter fields. Okay. So yeah, so let me just stop. Like here would be the end of the lecture and the end of the course. We can now discuss if you like, but I want to be maybe a bit more provoking from the philosophical side and ask the following. Now, if we force ourselves in some way to think about the metric as being in the same category as other kinds of fields, like electromagnetic field, matter fields, and so on, we can even ask a more profound question. And this question is whether is it even meaningful to distinguish between the geometrical structure or the space-time structure, better said, and the matter fields to begin with. Does this even make sense? Because we have seen here that there seems to be something hard to accept that we can distinguish between the metric as being part of the background structure, being a part of the matter fields, and so on. So it doesn't seem to be perfectly clear in this view of the relativity principle. So even before to even ask this kind of questions of that I did during this lecture, we could even ask, is there some meaningful way that we can discriminate in a physical system to say that something is part of the space-time structure and something is part of the matter structure? Okay. And so if I will finish with a bit of publicity. I am part of the UPA group in Utrecht, and one of the main projects of our group is what is called the CosmoMaster project. It's led by Niels Martins, and the main core of the project is to really take this claim that I said for and doubt it. So we say that in the view of modern physics, and we have different case studies, inflation, spin to gravity, black holes, dark matter, dark energy, can we really discriminate in a meaningful way, like we try to do with, for example, with the principle of relativity, if there is a clear notion between matter and how matter has to behave, and space-time and how space-time has to behave? We claim in principle that this is not clear, and we are trying to find ways of showing that in the precise manner. So just if you want to check, we have a webpage in the Utrecht University, the UPA group. We do a lot of seminars and colloquia with different aspects, not only about this, obviously, but of philosophy of cosmology, of space-time, of quantum mechanics. And we have online seminars almost every Tuesday. And now we are on vacation, but in September we will start again. So if you want to join, just visit the webpage and or even write us an email or anything. So with that, I finish here the third and last lecture, and I'm very open to questions and even more to debates. So if you have any strong opinion that you think this is not true or any other idea, this is really more than welcome, because it's always nice to have other opinions. Okay, so I finish here.
Well, thank you very much, Antonio, for this lovely course that you gave us. And I think on behalf of the audience, like I said, it was extremely provocative and clear as well, because I think we're exposed to words as physicists, we're exposed to phrases like general covariance principle, even equivalency principle for that matter, and not with sufficient clarity or attention for that matter.
Yeah.
So let's welcome everyone to ask questions. I see, for example, in the chat, I can see two questions. One by Pedro Kess asking about the last slide, but as the question came out, you were still talking about it. So if it's anything not clear, you can unmute yourself and ask for further clarification.
I just didn't quite understand the meaning of this phrase here, the statement.
Yeah, I mean, so it's maybe I misspelled some parts, but what I was trying to say is that if we want to save the principle of relativity, as Einstein proposed it, as trying to relativize space-time, I don't know if you remember the sentence that he said, I wanted to take from space-time all the objective notions possible. If you want to accept that to the last consequence within GR, then you are forced to conceive the metric as something that it's dynamical, in the sense that it's not absolute, it's not part of the absolute space-time structure, but it's part of the dynamical structure, just as the other kinds of tensors are, or the kinds of matter components, for example. To do that, okay? And then you can say, okay, my only absolute notion left, the manifold structure, that is invariant on the all coordinate transformation, and I can incorporate it as in special relativity with the Lorentz transformations, and as in Galileo, Newton's theory with the Galilean transformations. So this is the picture, yeah.
Okay, thanks.
And there is also someone, I think, responded to the provocation. Someone wrote, "So implying that the matter field and the space-time structure are somewhat similar." And that's it. That's the observation.
Yeah. Yeah, I mean, this is what it's pointing towards, and actually one can even think, extend this and think, well, GR tells us a bit about that, right? Because we have, for example, gravitational waves, which they do seem to be as electromagnetic fields, right? So what thing makes the metric special from matter? Well, I argue that there are some distinctions. For example, the metric gives us some causal structure, which other kinds of fields does not give us. So actually, this is more in the line of the project that I'm working on, which is doesn't tell. It's I'm not saying that the metric is matter. I'm saying that this whole distinction, which started with Einstein trying to dilute concepts, saying, no, this is not, this is relative, this is relative. Well, maybe we argue that even the whole picture of matter and space-time is diluted in the modern framework, right?
Yeah, I think I sympathize with this observation, because the demand that the metric to be invariant, I mean, isometries, to look for isometries, in other words, it's quite a stricter demand. And as you mentioned yourself, if you want to start to look for particular solutions, you can't dissociate that from the matter content if you believe in general relativity. So yeah, it does seem everything seems to be interconnected in an interesting way, especially once we learn that this geometrization as you showed in the first lecture, is not necessarily an exclusive feature of GR. So this is
exactly.
tricky.
Yeah.
Any more questions? Any more questions to Antonio?
Yeah, otherwise, if you need time to reflect about this, you can send me an email or
Thank you. Really generous. But let's give it a final push for the final chance to ask that in lecture. If anyone has anything to say or a comment. Well, apparently not. So let's thank Antonio once again for this lovely course he gave us. And yeah,
it was a pleasure.
See you everyone. Goodbye. Thanks for attending.
Bye. See you.